Hello, I'm going to present to you STM32N6 STEdgeAI-Core command line development pipeline. What does it mean? The target of this lab is to show you how to develop, pre-train and 8-bit quantized deep learning model using STEdgeAI-Core command line to be integrated within STM32N6 microcontroller embedded project, in particular using neural processing unit as a peripheral, as a coprocessor of N6 microcontroller. As an example model, we will use tiny Yolo v2, so the object detection model, quite well-known one. What I understand by development pipeline? I mean 3 steps: generation or compilation of the deep learning model to the C code representation to be executed on STM32N6 microcontroller, in particular using neural processing unit, then validation of the model execution on N6 microcontroller. In this case, we need real hardware, and it will be STM32N6 570DK board, and finally providing the model execution. So for example, see what is the real memory bandwidth using the same board. First of all, we need to go through the prerequisites of the lab. So the mandatory point is, of course, PC or laptop running 64-bit version of Windows 10 or 11. You need administration rights for software and drivers installations. You need USBC port and USB-C cable to connect N6 development board. Of course, you need N6 board. Here you can see the landing page on the SD web page of this board. So it is discovery board, and on the picture you can see board is equipped with display and camera. This is 5 megapixel camera. And also, to clarify, we are going to list all the links I'm using as hypertext in the description of this online course. We need STM32Cube IDE version 1.18.0 to be installed. We need also STM32Cube programmer, and of course we need STEdgeAI-Core repository version 2.2 to be extracted in the root/st folder. So the landing page of the repository is here, and you need to scroll down and download Windows version here. Important point, after installation of STEdgeAI-Core, is to modify all the paths and parameters of config.json and config_n6l.json files. Those files are located in the STEdgeAI repository in n6_scripts subfolder. I can show you. So we are in the /st folder. Then I'm going to the STEdgeAI repository 2.2 version, and then scripts folder and n6 scripts subfolder. So you can find both config.json and you can find config_n6l.json files. The detailed description of the configuration file is in the N6 loader configurations of STM32N6 NPU getting started document. I can show you. And you need to scroll down a bit. And find N6 loader configurations. So here you have a relevant subsection for the config.json, and scrolling down, the next subsection is for config_n6l.json. Also, I'll put detailed example of the config.json on this slide, so you can perform a screenshot. So as you can see, for example, cube ID is indeed 1.18.0 and is located in /st folder. And next slide, it is the config N6 LJSON, so we can again perform screenshot. Then let's come back to the prerequisites. So the last action is to download or clone STM32 Model Zoo Services repository, because during hands-on we are going to focus on the application code from this repository. So I can show you. This is STM32 Model Zoo Services main, also in /st folder, and there is an application code and object detection use case. There are also another use cases, but today we are going to focus on object detection. And of course, N6. I explain content of this folder later on. So the landing page of the Model Zoo Services is here, and you can go to the code button and just download zip, or if you prefer, you can clone repository. Okay, we are done with the prerequisites. Regarding discovery board, during this lab, we will be using only development boot mode of the board, because there are two boot modes of the N6 microcontroller as a flashless microcontroller, development boot and flash boot mode. So regarding development boot mode, you need to configure the boot switches accordingly. It means in practice that boot 1 switch must be in position close to the edge of the board, close to the H label of the switch. There are several ways to access, to interface to the STEdgeAI-Core backend. The online tool, so web interface, so-called developer cloud, then local graphical interface, so-called STM32 CubeAI as a plugin of STM32 CubeMX, and our use case, the command line interface. However, please have in mind that backend is still the same. Let's focus a bit on the model generation or compilation. So this is first development pipeline step. The entry point for the STEdgeAI-Core backend using command line, it is stedgeai.exe command. Then you need to add operation to be executed. In this case, this is generate, then model file name, the target MCU, if the NPU neural processing unit should be used or not. By the way, STNeuralArt, it is equivalent name of the neural processing unit. And finally, you need to port the JSON file containing the configuration of the compiler. This is the flow of the compiler, and to clarify, for the N6 microcontroller, in fact, you need two compilers. One classic compiler, well known for the core, in this case it is Cortex M55, so for example GCC compiler, as we are going to use today, and compiler or backend for the deep learning model. And this compiler, so-called Atom compiler, so Atom, it is another equivalent name of the neural processing unit, compiles both for the neural processing unit hardware, and if given operation of the model is not supported by NPU hardware, the compiler takes care about delegation of this operation in software way to be executed on Cortex L55. As you can see, the input format for the NPU compiler, it could be TensorFlow Lite, quantized model, 8-bit, and ONNX quantized model. Again, to remind you, we expect 8-bit quantization because currently the STEdgeAI implementation supports for the neural processing unit of N6 supports only 8-bit fixed point computations. Another companion input for the compiler, this is the option files already discussed here, and memory pool description. So let me show you an examples of those two files. So we are in application code folder of the Model Zoo Services repository, then object detection, then N6 use case, and we are entering model subfolder. So the configuration of the compiler is here, user neural art STM32N6 570DK JSON. DK because we are using a discovery board. It is also an option to use Nucleo board. So let's open this file. So you can see when the file is quite simple. As a first action, it points out to the memory pool file, so the description of the memory pools of the N6 microcontroller. And the second entry is related to options to the compiler. For example, you can see the level of optimization. You can see enable virtual memory pools, what means continuous address space to be seen by compiler. Enable epoch controller to increase in the performance of the model execution. Because just to remind you, the N6 is equipped with the hardware sequencer, which unloads the Cortex-M55 core when executing deep learning model step by step, epoch by epoch. Okay, so it was configuration file for the compiler. And now in the subfolder my mpools, you can find the memory pool description files, and in our case it is DK board. So this file, so we can see memory pool description. Let's focus on the AXI SRAM3 description as an example. This SRAM from 3 to 6 is dedicated for the neural processing unit. By dedication, I mean connection using high-speed 64-bit bus up to 900 MHz clock. And indeed, you can see the throughput is labeled as high, the latency is labeled as low. So we can review another example, XSPI2 interface. So we can expect a bit of bottleneck. This is octoflash, so the location for the memory initializers for the weights of the model. And indeed, throughput is medium and latency is high. Output from the compiler, it is .c file to be integrated within the project. This file contains the NPU configuration and of course memory initializers, the weight of the model. You can also analyze in detailed compilation process thanks to the report files. Just to be aware, there is also internal ONNX file representation because this is the first pass of the compiler to optimize the layers of the model, creating the intermediate ONNX file. And then there is a second pass of the compiler to compile this intermediate ONNX file as a C code. The detailed documentation can be found under this link. So we explain briefly the compilation, the generation step. What about validation of the model? So it is possible thanks to the AI Runner Python package. It allows both the validation and profiling of the deployed on the target hardware C model. And there are two configurations. The model can be executed both on the host, so we have the highest possible accuracy, and the model can be executed on the target hardware thanks to the AI validation firmware uploaded to the board. Why such an approach? So having model executed on the host and in parallel model executed on the target hardware, we can consider the model executed on the host as an original model, so our reference, while the model deployed on the target hardware performs prediction, and we can compare the results using input dataset, and by default this input dataset is random. So finally we will get the relative metrics. So this is the default and the first configuration of the validation flow. There is a document describing in details the validation process, also the metrics. So you can see detailed description of the metrics like accuracy, root mean square error, L2 relative error, etc. And this figure is already known to us. So this is the default configuration of the validation, original model execution, C model execution on target hardware, and comparison of results using random data. However, it is also possible to provide user data, and it is also possible to skip the original model execution and provide the ground truth data as a reference.